Hello. As randomness is inherent to complex systems, including urban systems as we'll discuss shortly, in this video let's review the basics of statistical analysis that can help us account for randomness, specifically the idea of a random variable and its distribution. So statistical analysis deals with randomness. But what does the randomness have to do with the cities, which are literally built in stone, or at least wood, and with the city residents who do not act randomly but rather purposefully? But first, let's get defined with the terminology. What shall we understand by randomness, particularly in urban context? Philosophically, one could distinguish the true randomness, where the outcome of the process is fundamentally unpredictable, and the perceived randomness, when the causes of the outcome are just not understood or are intractable for us. Like when we roll a dice, its movement is fully controlled by the initial impulse we give it and the laws of physics. But the nature of the process is so complex for us that we can't effectively predict the outcome. So while the process is not truly random, its outcomes are unpredictable for us, and therefore, so perceived randomness is simply the lack of information or inability to predict. While the true randomness, to be honest, remains primarily a philosophical concept. We can't even know for sure if it does exist. Maybe it does, for example in the quantum world, like a position of a particle before it is observed. But from a practical standpoint, perceived randomness is indistinguishable from the true randomness. So either way, we don't know the characteristics of interest or can't predict them before we observe them. This way, perceived randomness is very common for complex systems. And urban systems serve as a perfect example, as clearly their functioning is way more complex than rolling a dice. In such systems, there are often so many factors impacting any given event or quantitative parameter of interest that its true causes remain hard to track. For example, take an arbitrary house. Can we know its price if it's missing in the data? It's not truly random, as the sale already happened, but before we get the data on it, we can't know the price for certain. We can make certain inferences based on the known characteristics such as house size, amount of land, neighborhood, etc. But even if we know a lot about the house before we learn all the factors that played a role in the deal, for example, was it a foreclosure, or was the seller in the urgent need of money, how the buyer negotiated, etc., we can't be certain about the price. It still remains random, at least to some extent, until we learn it. But does acknowledging the randomness for the quantity of interest means we don't know anything about it? Well, randomness only means we don't know everything, but it doesn't mean we don't know anything. Let's say we are waiting to see the next person on the street and guessing how tall the person is going to be. You don't know for sure, and this way we can call the height of the person a random variable, which can apparently take different values. But we can assume some reasonable range of like between 5 and 6.5 feet for it. And from statistics you can make further inferences of which height or value of the random variable is more or less probable. Unexpected outliers are of course still possible, but rather rare. So the randomness is not completely random. How we quantify it? We use the concept of probability here. Again, there are two approaches to defining and understanding the probability. The frequentist approach, basically drawing conclusions from historic observations, counting the observed frequency of the event, and trying to extrapolate it to the future. And Bayesian, where the probability represents our degree of confidence that the event is going to happen based on both theoretic considerations and empiric data. For example, when tossing a coin, we can assess the probability of getting a heads up as 50% based on tossing it 1,000 times before and getting it 500 times heads up. This would be a frequentist approach. Or we can also conclude so based on the knowledge that the coin is fair, or the opposite, based on the lack of any knowledge. This way, not allowing us to prefer heads over tails or otherwise. This, in short, would be the Bayesian approach. It's quite useful when empirical data is absent or by itself is not sufficient to draw any reliable probabilistic conclusions. For example, what would be a chance for a hurricane stronger than Sandy to hit New York City next year? As we don't have an observed history of such hurricanes, we can't really tell. From the frequentist standpoint, it will be zero. Yet, it did happen in 2012. And the Bayesian approach, using the theory about hurricane emergence and movements, could have given a more reliable risk assessment. And Bayesian approach can actually involve both prior theoretic considerations and further empirical data to confirm or adjust those.